We're continuing our look at acids and bases, focusing on Bronsted-Lowry. In our previous videos, we talked about relative strength of acids and bases as measured by pKa values, and we talked about acid-base reactions and using pKa values to predict the position of equilibrium. What if we don't have a table of pKa values? In some cases, we can still determine relative acidity based on structural differences. So in this video, we'll be focusing on how structure affects acid strength. If we don't have available a table of pKa values, what kind of information can we get about relative acid strength? We want to consider how structure can affect acid strength. If we were to compare our acidic proton connected to different atoms, so hydrogen connected to fluorine, oxygen, nitrogen, carbon. Notice we're comparing across the periodic table. What can we determine about their acid strength? Well, actually, we're going to consider the conjugate base. So if a base grabs off a proton from CH4, we will be left with CH3 with a lone pair on the carbon and a negative formal charge. For ammonia, we're starting out with one lone pair. If a base grabs off a proton, we will have NH2 with two lone pairs and a formal charge of -1. For water, we're starting out with two lone pairs. If a base grabs off a proton, we will have hydroxide as the conjugate base. And in the case of HF, if a base grabs off a proton, we will be left with F-. Oops, because we're starting with three lone pairs on the fluorine. Now, as we are thinking about trying to assess acid strength, we want to consider the stability of the conjugate base. Now, this analysis doesn't work for all types of reactions, but it does work with acids and bases. If we think about the relative stability of our product, the more stable our product is, the more reactive the starting material is. So the more stable the conjugate base, the easier it is to form, which means that the original acid is a stronger acid. So in terms of electronegativity, we know that fluorine is more electronegative than oxygen, which is more electronegative than nitrogen, which is more electronegative than carbon. So as we compare these conjugate bases, fluorine is the most electronegative, so this is the best able to bear that negative charge. Oxygen's not quite as good, nitrogen's not nearly as good. The carbon, this is pretty bad at holding a negative charge. So this is going to be very unstable, and as we move this way, it becomes more stable. That means then that in terms of relative acid strength, we know that HF is going to be the strongest acid, followed by water, followed by ammonia, followed by methane. And if you'd like to put a number to that, HF has a pKa of 3.1, water is 15.7, ammonia is 36, and methane is 60. So a significant difference in pKa values, and as we are comparing across the periodic table, the strength increases as the electronegativity increases. Now looking at it in the other direction, the relative base strength, because CH3- is very unstable, it doesn't want to exist as the CH3-. So it really wants to act as a base. It really wants to grab off a proton from anybody. And so that means this is a very, very strong base. So our CH3- is the strongest base, followed by NH2-, followed by hydroxide, and then our weakest base is fluoride. right? And that should make sense because we just said that this is the most stable, it's best able to bear that negative charge. Well, this is perfectly happy having a negative charge, maybe not perfectly happy, but the least unhappy of all of these. It's not feeling desperate to grab a proton to get rid of that negative charge. So as we think about how structure affects acid strength, as we are comparing across the periodic table, we want to focus on electronegativity. The more electronegative the element, the stronger the acid. Let's look at another example of how structure affects acid strength. And in this case, we're comparing the halogens. So HF versus HCl versus HBr versus HI. Well, maybe this one also goes according to electronegativity. So I think HF is going to be the strongest, followed by HCl, followed by HBr, followed by HI, because electronegativity, fluorine is the most electronegative, followed by chlorine, followed by bromine, followed by iodine. But what's observed is the exact opposite. HI is the strongest acid, followed by HBr, followed by HCl, followed by HF. Notice now we are comparing down the periodic table, and as we compare down the periodic table, we are not using differences in electronegativity. Instead, there are two ways we can think about this. So to assess acid strength as we're looking down the periodic table, one thing we can consider is bond strength. We want to compare the relative strength of the HI bond compared to HBr, compared to HCl, compared to HF. Whichever bond is the weakest is going to be the easiest to break. Let's look at HF compared to HI, and we could represent the HF bond like this, and the HI bond, maybe it's going to be more like this. If we think about it in terms of atomic size, our hydrogen compared to fluorine, we're going to have some decent orbital overlap. That gives us a short bond, and so this can be a relatively strong bond. But with HI, here's our little hydrogen atom, and then here's our great big iodine. And so this orbital overlap isn't going to be that good. The iodine barely knows it's there. And if we were to think about the bond length, we're going from the center of the hydrogen atom to the center of the iodine, and that makes it a really long bond. So in terms of bond strength, HI is going to have the weakest bond, so that one should be the easiest to break, making this the strongest acid. Within HF, this is the shortest and strongest bond, making it the hardest to break, making this the weakest acid. So by considering bond strength, this order makes sense. Another way that we can assess acid strength, and this is the same as what we did on the last slide, is to consider the stability of the conjugate base. We're thinking about I minus compared to Br minus compared to Cl minus compared to F minus. We know that fluorine is the most electronegative, so we might expect that this is going to be the most stable. But because we are comparing down the periodic table, we're talking about a significant difference in size. So once again, let's think about our extremes, and maybe this is our fluorine, and this is the conjugate base, this is the fluorine ion, and it has the negative charge pretty concentrated in a small space. In contrast, when we have iodine, here's our iodine ion. Even though iodine is not nearly as electronegative as fluorine, once this great big ion has a negative charge, it barely even knows. This charge is so spread out, because remember, we're talking about a big squishy cloud where these electrons are likely to exist. So having an extra electron in this huge space, iodine barely even notices. So as we compare down the periodic table, we have to focus on size. So both in terms of bond strength and in terms of the stability of the conjugate base, our relative acid strength, HI is the strongest, followed by HBr, followed by HCl, followed by HF. And then thinking about it in terms of relative base strength, F minus is going to be the strongest base, followed by chloride, followed by bromide, followed by iodide. So what we've seen is when we are comparing structure and how that affects acid strength when we're making our comparisons along the periodic table. If we're comparing across the periodic table, we focus on electronegativity. If we're comparing down the periodic table, we focus on size. So far, we've been comparing structure and acid strength, making comparisons either across or down the periodic table. But if we look at these examples, our most acidic hydrogen is connected to, in this case, oxygen, in this case, oxygen. So they're connected to the same element. So we're not comparing across or down the periodic table. So what do we consider instead? If we are making comparisons with our acidic proton connected to the same element, then to assess acid strength, we need to consider inductive effects, and or resonance effects. With inductive effects, we are talking about attraction for electrons through bonds and to some extent through space. So this is really closely related to electronegativity. But one important feature of the inductive effect is that it falls off quickly with distance. It falls off quickly with distance. If we look at these two acids, so they're both carboxylic acids, which have the C double bond O OH, C double bond O OH. Over here, we have a CH3 group. Here, we have almost the same CH3 group, except one of the hydrogens is replaced by a chlorine. Well, we know that chlorine is more electronegative than carbon, so that means that chlorine is going to be pulling away electron density from that carbon. To a lesser extent, it's going to be pulling away electron density throughout the entire molecule. So to think about how inductive effects affect the acid strength, we can either think about it in terms of the acid itself. Here we have a particular bond strength for our oxygen hydrogen. And here, because chlorine is pulling away electron density, it's going to be pulling a little bit of electron density all the way down here, which is going to slightly weaken this OH bond, making it easier to break. And so that would make this one a stronger acid because of inductive effects. Another way to think about it is from the perspective of the conjugate base. So here is our CH3, C double bond O, O minus, compared to CH2, Cl, C double bond O, O minus. We know that chlorine is going to be pulling away electron density from that carbon. Well, this carbon can try to pull away a little bit of electron density from this carbon, which can kind of try to pull away electron density. I mean, oxygen's more electronegative than carbon, but any little bit is going to help. And so the fact that this is pulling away a little bit of electron density is just going to help a little bit to spread out this negative charge. And whenever you can spread out the negative charge, that's going to stabilize that ion. So because of this electronegativity, this is going to be slightly more stable, making this a stronger acid. Now the difference here, we're talking about a pKa of 4.7 compared to 2.9. Now, what does this mean that it falls off quickly with distance? Well, let's say we were looking instead at, here's our C double bond O OH. If this was a CH2 and this was a CH2, and this is where the chlorine is connected. So instead of being on the carbon directly connected to the acid, if it's on a carbon that's connected to a carbon that's connected to the acid, this is going to have a smaller impact on the acidity of this hydrogen. So this one has a pKa of 4.0. So more acidic than this one, but not nearly as acidic as this one. Now, in our other example, we have the same carboxylic acid, and then here we have an alcohol. So it's got the OH, but it doesn't have the C double bond O. So let's write out the conjugate base for each of these. So for the first one, we have the CH3, C double bond O, O minus, and I'm going to fill in some details. Let's fill in those lone pairs. And over here, we have CH3, CH2O minus. In this case, we have the negative charge on the oxygen. Oxygen's pretty electronegative, so that's okay. But that charge is just sitting there on the oxygen. Okay, these carbons aren't helping very much. Here, we have a negative charge also on the oxygen. Okay, that's all right. But notice, next to this group where we have all these extra lone pairs, we also have a double bond. So this is where I want you to think about resonance. We could imagine these electrons move in here to form a double bond between this carbon and this oxygen. And at the same time, these electrons would have to move up here to give an extra lone pair on this oxygen. So we can draw a second resonance structure that looks like this. In other words, we have a resonance hybrid where we have our CH3, COO, partial double bond character, a partial negative on this oxygen, and a partial negative on this oxygen. So while here, this negative charge is concentrated on one oxygen, that same negative charge is spread out along two oxygens. The more we can spread out our charge, the more stable this species is going to be. The more stable this is, the easier it is to form, which means this is our stronger acid, much stronger than this one. Here are pKa values. This is still 4.7, and this one, ethanol, has a pKa of 16. So definitely a weaker acid. This is the stronger acid because of resonance. Now let's see if we can apply what we've been talking about in the previous few slides. Can we predict the products of the following acid-base reactions? And then can we indicate the position of equilibrium without using a table of pKa values? Well, with our first example, because this one has a negative charge, this is probably going to act as our base, and therefore this is going to be our acid, and in particular, this is the most acidic proton. So this base will grab off a proton. These electrons will move on to the oxygen, and that will give us CH3, C double bond O, O minus, and F, CH2, C double bond O, O, H. Before thinking about the position of equilibrium, let's make sure we can classify our different components. This was the acid, and this was the base. This is the conjugate base, and this is the conjugate acid. So if we want to compare the position of equilibrium, we need to think about this acid compared to this acid. If we don't have a table of pKa values, we have to rely on structural differences. Now they are both carboxylic acids where we have the C double bond O, OH, C double bond O, OH. Here we have a CH3, and here we have a CH2, and then instead of a hydrogen, we have a fluorine. Well, we know that fluorine is very electronegative, so this is going to be pulling electron density away from this carbon, which is going to be trying to pull away from the rest of the molecule, which is going to weaken this oxygen-hydrogen bond, making it easier to break, which means this is going to be the stronger acid. Another way we could think about it is comparing the bases. Here, this negative charge is going to be spread out on both oxygens by resonance. Here, this negative charge will be spread out on both oxygens by resonance, but we also have this electronegative fluorine, which will be pulling away electron density by inductive effect, further spreading out the negative charge, stabilizing this base even more. If this is the more stable base, that means that this is the stronger acid. Therefore, the equilibrium lies to the left. In our second example, we have water and HS minus. So this has to be the base, grabs off a proton from water. So if the S uses a pair of electrons to grab off a proton, that is going to give us HO minus plus H2S. And let's label our components. This was our base, this is our acid, this is our conjugate base, and our conjugate acid. So we need to compare this acid and this acid, but we don't have pKa values. Well, what's the relationship between oxygen and sulfur? They're in the same column of the periodic table, but sulfur is below oxygen. So we are comparing down the periodic table. So as we compare down the periodic table, size is the most important factor, and because sulfur is larger than water, this is going to be the stronger acid, and water is going to be the weaker acid. So once again, the equilibrium lies to the left. So even without the pKa values, we can still determine the relative position of equilibrium. And finally, we have two examples that we already looked at back on slide 12 when we were using pKa values. But let's try again to find our answers just relying on structural differences. So looking at the first one, hydroxide must be our base, and so this has to be our acid. Now, if we think about an OH compared to a CH, we know that OHs are going to have more acidic hydrogens because oxygen versus carbon, we're comparing across a periodic table, so we focus on electronegativity. But what about comparing this OH compared to this OH? Well, that means this hydrogen is connected to an oxygen. This hydrogen is also connected to an oxygen. But we have differences in terms of resonance. If this acts as an acid, then the conjugate base has a negative charge on the oxygen, and that negative charge is just stuck there. If this acts as the acid, then that negative charge is on the oxygen, but it can be stabilized by resonance. And so this is the more acidic hydrogen, much more acidic than this one or either of these. So when hydroxide acts as a base, it is going to grab this proton, giving us this as the conjugate base and water. In our second example, we have this compound with an alcohol and an amine, and it's reacting with HCl. So this must be our base, and this must be our acid. And the carbons, these can't be bases because there's no lone pair for it ready to share, but oxygen or the nitrogen could both potentially act as bases. So we need to decide which one of these is the stronger base. Now, if we wanted to compare an alcohol and an amine to think about who is the stronger base, we could focus on their conjugate acids, ROH2 plus versus RNH3 plus. For these acids, the acidic hydrogen is connected to oxygen versus nitrogen, so we are comparing across the periodic table. As we compare across the periodic table, electronegativity is the most important factor. Because oxygen is more electronegative than nitrogen, we know that this one is going to be the stronger acid, and this one is going to be the weaker acid. Because this is a stronger acid, that means the alcohol would be the weaker base. Because the ammonium ion is the weaker acid, that means the amine would be the stronger base. So in this molecule, this is going to be the stronger base. So when this molecule reacts with HCl, this is going to grab the proton. And that will give us this as the conjugate acid, as well as Cl-. So in a previous video, we determined which one of these was going to act as the acid, which one of these was going to act as the base by using pKa values. If we don't have pKa values, we can still determine which one of these would act as the acid, which one of these would act as the base, just by using structural features.